All right, so I finished my general announcements, reminding students that the Section 3.1 textbook work is dead today, or tomorrow, excuse me. And same thing with the online 3.2 quiz. If you haven't taken that, you have one more day to get that done. Retakes will be available for a week starting tomorrow. Okay, the only thing due this week is the linear regression packet. Remember that we do have the Chapter 3 test coming up next week on Wednesday. Okay. Now, I already gave you all some time to complete A and part of B. So we basically have a scatter plot that relates the weight of a person to the height of a person. Okay, in part A, the highlights were because you didn't have access to correlation, I'd be lenient on whether you chose to describe the strength as weak or moderate. But again, please don't come up with like versions of these words that are combined. Like, don't call it moderate weak. There were some folks, mistake by the way on the Canvas quiz, there were some folks that determined that the correlation shown in the scatter plot was moderately strong. You lost credit for describing strength because you didn't pick a term. By the way, the correlation was 0.9, 0.92, I think. So you had to use the word strong. That was required. Okay. Now, with part B, I asked you all to just do the math. Remember, I said to show the work. Okay, this is what I mean by show the work. We're predicting that a 5'0" or 60-inch person is going to weigh about 121 pounds. We're predicting that a 6'8" or 80-inch person is going to weigh about 186 pounds. You're told to sketch the model. What I'm trying to walk you into slowly, and this is why I said don't graph the line yet. I saw some of you sketch the line of best fit, and don't get me wrong, your line was probably reasonably accurate. But the way you're expected to graph a line, especially when you have access to a model, maybe you remember this from geometry. How many points do you need to define a line? 2. So graph 2 points and connect them. That's the expectation. You're not estimating where the line is. You have some reasonable estimation of where the points are. So this is what you're supposed to do. Okay, you now know that you expect a 60-inch person to weigh just over 120 pounds. You expect an 80-inch person to weigh right around 186. You graph those 2 points. Where those 2 points are located is somewhat subjective. It just needs to be reasonably close. But that is how you create the line of best fit. You connect those 2 points. Now, by the way, if the question down at the bottom in part B didn't give you the heights of 2 specific students, okay, if it didn't say find the expected weight of these specific people, you could use any heights you wanted. If it just said sketch the line of best fit, there's a mathematical process for that. Pick two heights, predict their weights, graph those 2 points. And if that's what you did, you'll notice that those 2 random heights that I picked also fall on the exact same line. Okay. So if part B didn't give you 2 specific people to focus on, but just said sketch the line of best fit, the strategy is find 2 points you know should be on the line and connect them. Okay, that way everyone in the room is basically getting the same line. Questions? All right. So we're going to go through a couple of the standard practices that we talked about last week. One says interpret the slope in context. Remember this old idea of rise. First of all, you have to be able to identify the slope. And one thing I said before is that slope is the number attached to your variable. So this would be your slope. Okay. So I'm going to tell you right now, in your interpretation of slope, if you don't have the number 3.26 somewhere, you're not getting full credit. You have to give that number. Now, going back to the graph, remember rise over run, it's, okay, how much is this unit changing for every one change in that? Okay, so how much do you expect the weight change every time by 1? That's what the slope means. Okay, so this is 3.26 pounds per inch. So if you say something like this, full credit. I expect a person to weigh 3.26 pounds more per inch in height. And by the way, you can use any multiple of that if you want. You know, if you wanted to multiply both of those numbers by 10 and say, I expect a person to weigh 32.6 pounds for every 10 inches they grow. No problem. You get full credit. This is one of the ways, by the way, I would have fun and torture the AP grader if I was taking the AP exam. I would take both of those numbers and multiply them by pi and then say, all right, I expect you to go up by this many pounds for every pi inches you grow. I'm going to get full credit because it's the right answer. Okay, but don't go out of your way to torture yourself that way. Now, if you say something like this, it's going to feel like you're saying the right thing. A person is expected to gain 3.26 pounds as height increases. That's not specific. So if this person goes up 1 inch, you expect their weight to go up by 3.26 pounds. And if that person goes up 5 inches, you expect their weight to go up 3.26 pounds. As your height increases, you gain 3.26 pounds. My question is, as height increases, by how much? Okay, so this doesn't define the run. It says the rise is 3.26, but it just says if the run goes. It's like, okay, but by how much? That's the thing that's missing. All right. Now, the reason I specifically added part D to this is because what we're going to learn tomorrow is how to calculate a line of best fit. Okay, right now, the only real method that I've given you for knowing the equation of a linear model is A, it's given, which is what happened here. Okay, in the very first page, they give you the model in part B. Like, here's the equation, done. Well, that's not really any work for you. The other way that you're going to have access to a linear model is a computer printout. And I tried to sort of make that less intimidating and highlight the key features you needed to know. Okay, like by knowing the terms coefficient or constant. Okay, when you're looking at a printout, you basically pull out the two variables. So you would be able to look at it and know, oh, I'm using height to predict weight. You would be able to find the numbers negative 7.25 and the slope of 3.26. And you'd be able to find r squared, which you'd have to take the square root of to get r. Okay, so printout is the other method for knowing the model. The third method is what we're going to get into tomorrow, which is you have to actually calculate the line of best fit. But you do that using summary statistics. It's never going to be a situation where you have to type in 30 points into the stat plot of your calculator and run a linear analysis. No, there's nothing like that on the AP exam. There's nothing on the AP exam that requires a graphing calculator. I'm going to teach you how to use it because it can save you time. Okay, but there's nothing on the exam that requires a graphing calculator. Now, that being said, circling back to what I started, the reason I put part D in the packet is because what I find is students assume that when they get a y-intercept that makes no contextual sense, that they must have done something wrong. And that's not true. Okay. In this particular case, it says, does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. So this represents an expected weight. That alone doesn't make any sense. You can't weigh negative 74 pounds. But when would I expect a person, at least according to this model, to weigh negative 74 pounds? When they're how tall? 0. That's the whole point of a y-intercept. Okay, so we have a whole bunch of data. Our scale on the x-axis starts at 60. So please understand, this is not your y-intercept. I understand it hits the visual y-axis at around 121. But the y-intercept is defined as when the x value is 0. So you would have to trace this line back from 60 to 50 to 40 to 30 to 20 to 10 to 0, and then ask yourself, where does this line hit the y-axis back here at 0? Does that make sense? That's your y-intercept. Where does it hit the y-axis, the actual y-axis, when x equals 0? So this y-intercept of negative 74 pounds absolutely makes no sense in context, because a person can't be 0 inches tall, nor can a person weigh negative 74 pounds. Okay, now we're going to circle back to the interpretation of r squared, which I tried to warn you all last week, in my opinion, is the one thing that seems to be the hardest for kids to try to get right when they're writing about it. Okay, so the whole idea here is we are using a person's height to predict their weight. So your weight can be higher or lower, and there's a lot that goes into that. But the question is, how well does knowing height help me predict your weight? Your weight is going to fluctuate, and if I just know your height, how good of a job can I do at noticing or expecting or predicting how your weight is going to change? That's essentially what r squared is. Okay, so in this particular case, you take the square root, or you take r and square it, you get an r square value of 0.394. Okay, so you're given that r is 0.628. You square it to get r squared. Okay, by the way, an r value of 0.6 means weak. Okay, so again, visually in part A, I told you if you said weak or moderate, I'll take it. But now that we know what r is, if we went back to part A, if this question said, correct if needed your description in part A, well, if you didn't say weak here, you would now have to say weak, because you would know the correlation is 0.6. Okay, but in any case, the key idea here is changes in weight. However you want to write this, whether you want to write this, about 39.4% of variation in weight can be accounted for by variation in height. Or you could say variation in height explains about 39% of variation weight. Or you could say, this model explains 39.4% of variation seen in weight. Okay, or you could say 39.4% of variability in weight can be associated with variation in height. The whole idea is you're trying to predict weight. You're not trying to predict height. You use an actual height. You take an actual height and you use that to predict weight. So it's not variability in height that you're trying to account for. You get to control that. Do I think, are you 72 inches tall? Are you 52 inches tall? Are you 61 inches tall? I get to control that variable. But I use that variable to make predictions about how weight will change. So that's the key idea when you're trying to describe R squared in context. So part F says, how does the 5'9" student in this group compare to their expected weight? First of all, how many inches is 5'9"? 69. So we have a 69-inch person who weighs 140 pounds. Now, side comment that will relate to a common mistake I want to address at the end of this problem. Okay? So what I'm about to show you has nothing to do with this question except for addressing a common mistake I want to talk about at the end. If you were to add up all the weights of all 12 of these people and then divide by 12, in other words, if you were to calculate the average weight, you would find that the average weight of this group is 144.833 pounds. Okay? Here's a question, and it's not meant to be a trick question. Does that 5'9" person weigh more or less than average? Remember that. Store that in the back of your head for later. This person weighs less than average. Okay? All right. How does the 5'9" student compare to their expected weight? So what do we need to do? Use the equation and substitute what? Substitute what? Their height. Exactly. So you want to take their height of 69 inches, plug it into the equation, and say, oh, I think they're going to weigh 150.9396 pounds. Now, here's my next question. Does this person weigh more or less than expected? Less. Okay, so we have a person that weighs less than average. They also weigh less than expected. But let's really cement in our mind, those are two very different statements. Are you less than average or are you less than expected? Those are two very different benchmarks. Okay, here's the visual what's going on. We find this student on the graph. We say, okay, they are 69 inches tall. They weigh 140 pounds. But that is not what this model thought would happen. What this model thought would happen is that if you're 69 inches tall, you're going to be right there. That's what the model thought happened. Now, the difference between those is what we call a residual. If you are below what we thought you would be, you have a negative residual. I say that because what a lot of people get confused about is, okay, I thought you'd weigh about 150 pounds. Does that mean your residual is positive 10 or negative 10? This is a really common misconception. Okay, so please remember that when you're calculating what's called a residual, you always take the actual and minus the predicted. But if you don't want to memorize that pattern, just think about it logically. This person is less than what I thought they would be, so their residual better be negative. Okay, so when you're asking yourself with this 150.69 and they actually weighed 140 pounds, if you're asking yourself, should I do this or should I do this? My response to you is going to be, well, are they more or less than what you thought they would be? And you say, well, I thought they would be 150, but they actually only weigh 140, so they're less than I thought they'd be. Then I'm going to say to you, well, then their residual should be negative. Does that make sense? Common misconception is to reverse the order of subtraction. Okay, but it will always be what was your actual minus what we thought it was going to be. That will never change. That will always be true. Okay, a residual is actual minus predicted. RAP, R-A-P. Residual is actual minus predicted. Okay, so you would do this. You would subtract what is their actual weight minus their predicted weight, and you end up with a residual of negative 10.69. Visually, this is what we're talking about. That vertical difference between these two numbers. That's your residual. That's what we just calculated. Now, you're asked to calculate this, okay? And don't subtract in the opposite order. And remember that this person is 10.69 pounds under their expected weight. I'm going to pause to give you a chance to write, and then I want to address that common misconception I alluded to earlier. Okay, so a common wrong thing that I see a lot of kids write here is this person is 10.69 pounds below average. Wrong. You did not calculate an average. When you plugged in their height of 69 inches and you got a predicted weight of 150.69, that's not the average. That's what you expect a 69-inch person to weigh. Okay. So looking back up at the picture, let me bring the average back in. Okay. I will agree that that person is below average, but I'm not going to agree that they're 10.69 pounds below average. In fact, if the average is 144.833, this person is 4.833 pounds below average, but they're 10.69 pounds below expected. So just to be clear, if I were to graph the mean point, which is kind of, whoa, that's way too thick. Okay, go away. The mean point is right about there. Okay, so let's be clear on something. Anybody that is below that line, all of these people are below average. Okay, everybody above that line, all of these people are above average. Okay, however, let me undo this real quick. If you're going to focus your attention on the line, all of these people are below expected because the line defines what we expect it to be based on your height. And all of these people are above expected. And understand you can be any combination of those. For example, let me take away these highlights and highlight a very specific zone. If you fall into this zone here, you are below average. You weigh less than the average person in the group. And yet you are above expected. You weigh more than what the line predicted you would be. Does this make sense? Okay. And if you're, say, over here, well, now you're talking about people that weigh more than average. You're more than the average person in the group, but you're still less than what we thought you would be. So please don't get these words mixed up. Very often when people are supposed to write, this person is 10.69 pounds below expected, they write they're 10.69 pounds below average. And whether you realize it or not, those are two very different things. That's what I'm trying to impress upon you right now. That precision in what you're writing does count. Questions? All right, so we have a new context. This is actually what we're going to be using for the remainder of the class, both 3.26 and 3.27. It says, here's a scatter plot of weight versus height for students in an introductory statistics class. Men and women are represented by circles and squares. I understand that you all don't have color, so I tried to graph the points as circles and squares to help make the distinction a little bit. Okay. The first question says, describe the association of the scatter plot above. Can anyone throw out a word that you definitely use to describe? Positive, absolutely. I would say in general, the taller you are, the more you weigh. Linear, I don't see any obvious bend. I know the data is scattered in kind of a weird way, but there's no obvious bend. So I'm okay with saying data is linear enough. What about strength? All right, so I'm hearing moderate. I'd be okay with weak. I think the only thing I wouldn't be okay with is strong. I think there's too much variability here to call it strong. So I said there is a weak, for those of you who said moderate, we don't have access to R, so I'm not going to be picky about that. There is a weak positive association that is linear enough and shows that taller students typically weigh more. Now, the last sentence is something that I'm going to try to draw after I give you a chance to copy. All right, so real quick, I just wanted to point out this last sentence. Also, the variation in weight increases as height increases. I think that's a advanced thing to notice. Okay, you can almost see, let me zoom out a little bit more. You can almost see how there's this sort of funnel effect where the points start out with a certain amount of variability that's fairly compact. I mean, yes, there are scattered points beyond, but as you get into larger and larger and larger heights, you end up with more and more and more spread. Okay. But backing up. Now, the next question says, comment on the differences between the men and the women. Let me get rid of all these crazy highlights real quick. There we go. All right, so part B says, hey, stop it. Comment on differences you see between men and women. Now, to help you all pick up on what I'd like you to pick up on, I'm going to cheat a little bit. First off, I can phase out the men completely. That way you can look at just the women for a moment. Okay, and what I'm going to do is I'm going to estimate as best I can a reasonable center for these women. Let's see, maybe right about there. I know I have the box somewhere hidden. There we go. Okay, so I tried to visually estimate where I thought the center of mass for the women might be, and then I put a box around all of the women. Okay, everybody got that? Now, if I do the same thing, but with the men, so let me phase out the women, and then I'll put a box around all of the men. Again, I tried to visually estimate where I thought the center of mass for the men were, and then I put a box around the men. Okay, so if you're going to talk about the differences between the men and the women, remember, you can compare the center of mass points. You can compare the size of the boxes for variability. So let's start with the center of mass points. What does that reveal about how men and women are different? The height and weight of males tends to be bigger. The males are centered at a higher height. The males are centered at a higher weight. So that is comparing the mean locations. Men on average appear to be taller and heavier than women. Now, in terms of variability, that's a little more challenging. Okay, but again, I'm going to try to show it to you visually. Can anyone tell me how the variability of men might compare to women? And I don't care if you want to focus on height or if you want to focus on weight. I'll take either one. Okay, so this is actually why I wanted to give you all the boxes. I'm going to cheat a little bit here. Remember, I put boxes encapsulate all the women and encapsulate all the men. If I slide the female box up, can you see how the two basically line up vertically? Okay, what does that suggest about the variability in weights? It's about the same. It's similar enough. However, if I adjust them horizontally, you'll notice that the male box is much wider, suggesting how does their variability in height compare? They're not similar. Yeah, but who's more? Don't say they're different. That's not specific enough. Men are more variable in weight, in height. Okay, so that's kind of what I would say here, that male heights vary more. Because the question says focus on differences, I put this next part in green. Variation in weight seems roughly the same. Okay, but you wouldn't need to say that because the question asks you to specifically focus on differences. All right, so here's where the part of the class is that I want to give you all a chance to figure things out for yourselves. What I will tell you is the answer to every question on the next page is no. But the challenge is, can you figure out why? Okay, so take about 6 minutes, see how far you can get on the next page. We'll go through it and we'll call it a day. Go. Okay, let me get you back real quick. So I warned you ahead of time that the answer to every one of these questions is no. Shh. I would say, in my opinion, the two that are the most objectively clear, thank you, would be A and C. Okay. B, I think, would be a more fair question if you had access to the correlation rather than visually determining that the relationship isn't all that strong. But with part A, we just a moment ago talked about the fundamental differences between men and women that are apparent in the scatter plot. So it would make absolutely no sense to fit an entire line to all of the data and try to make that one line represent both men and women. It would make way more sense to fit a line to the women and fit a line to the men and use those two separate equations to predict weight. So that's sort of my justification for this. I said, no, there are clear differences between men and women. Okay, if you're going to cite the differences, why would you use a single model for everybody? Break it into two separate groups and use two separate models. Now with part B, again, this to me is the one that's probably the least fair of these questions. All right, so what I said for part B is the association appears weak, so prediction would not be very reliable. This is the difference between is the model appropriate versus is the model accurate. Okay, so in part B, what I would say is clearly the women's group seems linear enough. I have no problem with fitting a line to that data and using it to make predictions. But should I trust that prediction? Probably not, because the relationship, what I'm thinking is, because I was thinking of how I could improve the packet, what I might do is provide the correlation for each of the separate scatter plots. That way, because my guess is that correlation is probably like barely weak. It's probably like 0.55 or something like that. And so the R squared value would be around 30%. That's not super accurate. Okay, you're not really accounting for a lot of the variation in weight based on the strength of that relationship. Now, the last one, this is, I think, the most objectively clear question on the page. Like, of the three, this is the one that should pop out at you as there's a problem with this. Okay? if you look at the data for males, the shortest males you have are 63 inches. So if you make a prediction anything shorter than that, you are extrapolating. You got it. So no, let me zoom in on this. No, this would be an extrapolation as the shortest man in this data set appears to be 63 inches tall. So instantaneously, you have a reason to doubt your prediction. Okay, I would say that is the most objectively clear reason to say no. All right, we're done. Thanks for watching. Have a good one.